Look at this closed container holding a liquid mixture of two components. The sky blue dots represent component A, a volatile substance, while the rose pink dots represent component B, which is less volatile. Below the container, a heating source is active. As we heat the mixture, molecules gain kinetic energy. Slower liquid molecules at the bottom absorb energy, break free from intermolecular forces, and escape into the vapor space above, a process called vaporization. Simultaneously, faster vapor molecules lose energy upon colliding with the liquid surface and condense. Soon, a dynamic equilibrium is reached where the rate of vaporization equals the rate of condensation and the pressure stabilize. To understand this vapor pressure, let's derive Raoult's law. At equilibrium, the rate of vaporization of a component is proportional to its concentration at the liquid surface, represented by its liquid mole fraction, Xi. Meanwhile, its condensation rate is proportional to its partial pressure in the vapor phase, Pi. Equating these rates, the partial pressure Pi is directly proportional to its liquid mole fraction, Xi. By defining pure vapor pressure Pi sat as the pressure when the liquid is pure, we get Raoult's law. Pi equals Xi times Pi sat. Dalton's law then tells us the total pressure P is the sum of these partial pressures. Let's visualize this total pressure on a pressure composition, or PXY diagram. The straight upper line is the bubble point line. It represents the pressure where the first bubble of vapor forms when depressurizing a liquid mixture. The curved lower line is the dew point line. It represents the pressure where the first drop of liquid condenses from a vapor. Between these lines is the two-phase envelope. Liquid and vapor coexist in equilibrium, connected by horizontal tie lines showing that the vapor is always richer in the more volatile component. Keeping pressure constant instead, we get a temperature composition, or TXY diagram. Here, temperature is on the vertical axis. The liquid phase sits at the bottom, and vapor sits at the top. The bottom curve is the bubble point curve, and the top is the dew point curve. Heating a liquid mixture at constant composition leads to the bubble point first, where boiling starts. Cooling a vapor leads to the dew point first, where condensation begins. In the real world, most mixtures deviate from Raoult's law due to unequal intermolecular forces between different molecules. We correct for this using the activity coefficient, gamma. When gamma is greater than 1, different molecules repel each other, creating a positive deviation. This repulsion raises the vapor pressure. A strong deviation forms a minimum boiling azeotrope, like ethanol and water, which boils at a lower temperature than either pure component. Conversely, if different molecules attract each other strongly, like acetone and chloroform, the vapor pressure is lower than expected, resulting in a negative deviation. This forms a maximum boiling azeotrope. Understanding these non-ideal VLE behaviors is essential for designing industrial separation processes like distillation.